There's a series of questions that often shows up on AP exams and college exams, and especially on the AP exam on the multiple choice where you don't have calculators to work, and sometimes it really gives students a tough time, or maybe they think they're not given enough information to solve those, and it deals with mixtures of gases and total pressures and partial pressures, and a lot of students want to either go in and solve that using the ideal gas law. They feel like they need a calculator, or maybe they feel like they're not given some information. Maybe the temperature or the volume wasn't given, so they don't think they can do the ideal gas law. Now, while mathematically there are some ways that if you had a calculator you could do that, normally these questions aren't given to be really difficult. They're meant to be pretty easy questions. And one of them that shows up fairly often is if we have a container, and in that container we have a mixture of helium and neon, for instance. So we got two noble gases here, helium and neon, and we're putting them in that container, and it normally will say something about equal amounts. Now, the first thing that we need to understand, if we do equal amounts of them, if we do 5 and 5, equal amounts means, in this case, the scenario that I'm doing here, equal number of moles of each gas. Well, if we have equal number of moles of each gas, then the 6 atmospheres of total pressure come from the 2 gases. And Dalton's law of partial pressures tells us that the pressure that helium contributes and the pressure that neon contributes will add up to the total. But it also, by way of taking Dalton's law and applying it with the ideal gas equation, we learn that those are proportional to the number of moles. So 5 and 5 tells me there's equal moles of these. So 3 atmospheres of pressure come from the helium, while 3 atmospheres of pressure come from the neon mixture that's in the container, because we have a mixture there containing equal moles. Now, where this question becomes a little bit trickier is occasionally this question will say we have equal masses of helium and neon. Now, equal masses does not mean equal number of moles. So it doesn't mean 3 atmospheres of pressure and 3 atmospheres of pressure. What we have to look at, if we have equal masses, we got to look at the molar mass. How many moles would that represent? Now, you can pick out a fictitious mass and calculate your proportions that way, or you can simply just look at the molar mass. Neon's molar mass is approximately 20. Helium is approximately 4, so that tells me that neon is 5 times more massive than helium. So if I have equal masses, since neon, a mole is 5 times more massive, that means one of these has the mass of 5 of the helium. So if I put equal masses in there, I'm actually putting more moles of helium in the container to make this mixture. So now when I want to solve for the partial pressures of each one, again, it is a ratio or a proportion. 5/6, 5 out of 6 of the pressure comes from the helium, 1 out of 6 comes from the neon. So in this scenario, 5 atmospheres of partial pressure come from the helium atoms in the container, whereas only 1 atmosphere out of the 6 comes from the neon. Another calculation that we sometimes encounter involves maybe 2 separate containers, or maybe 2 containers connected with a valve in the middle, and we're going to mix the gases, and maybe we want to know what the total pressure is when we're done, or how much pressure is attributed to each of the gases once the mixture goes together. So if in the container here on the right I have 9 liters of neon at a pressure of 2 atmospheres, and I just want to solve with regard to that gas in the container on the right, I know that P times V equals N times R times T, but I'm going to go ahead and solve that in terms of how much neon that we have in that container. So what we're going to call that is we're going to say N RT. N equals 18 over RT. And of course, R is the ideal gas constant. And on purpose in this, I didn't give a temperature, because if you had a temperature, then we'd want to use a calculator and go ahead and solve that mathematically. On the other side over here, I have helium. I have a smaller volume, but I have a higher pressure. So here we have pressure is 4 multiplied by volume of 3 also equals nRT, but I'm going to go ahead and rearrange that and say that N is 12 over RT. So in looking at this, for every 12 moles here, I have 18 moles on the other side, so then that tells me that there's 1.5 times the number of moles of neon. So I need to come up with some numbers here that makes this 1.5, so I think I'll use 4 over here to represent my helium, and then 1.5 times as much is going to give me 6 moles of neon over here in this container. All right, so then the question is, okay, so what's the total pressure when we put these two together? So if I combine these and go ahead and maybe open a valve in the middle and allow these gases to fuse through openings, and I end up with a gas mixture here. At this point, I want to go back and I want to go ahead and find, okay, what is the total pressure now that we've put all these together? Well, the easiest way to do the total pressure is to say pressure times volume. Now when I combine the two, the volume becomes 12 equals N, but I didn't have an N value. What I had for N was 12 over RT and 18 over RT, so I'm going to add those two up together, and I'm going to get 30 over RT, that's my N value, times RT. So these are going to cancel out, and I'm going to get here that the total pressure is equal to 2.5 atmospheres when I go ahead and combine these. Now, maybe we want to know how much pressure in that new container comes from, how much pressure comes from the helium, or how much pressure comes from the neon out of that. So my pressure, if I want to solve this for the helium, pressure for helium times the new volume of 12 equals N for the helium, which was 12 over RT, times RT. So again, those are going to cancel, and we're going to get that the pressure that comes from the helium is 1 of those atmospheres. Now we could apply Dalton's law here and go ahead and do a subtraction problem. We could subtract the 1 from the 2.5, but I want to go ahead and solve mathematically and show you the neon's pressure. Pressure for neon times the new total volume of 12 equals the moles of neon, which was 18 over RT, times RT. And so I get that the pressure for neon is 18 divided by 12, or the pressure for neon is 1.5. So if I look at this, these two should add up to be the total pressure, and they do. Now, going back to this, maybe we just wanted to know what percent of that pressure, or what mole fraction of that, or what fraction of that pressure came from each gas. We can go all the way back to here where we started, and we could have found that without going through the ideal gas law, because I can simply see here from looking at this that there's 1.5 times as much neon in this container. Then that tells me that that is attributed to the pressure from the neon. So we could look at this a couple of ways. We could call it the neon amount, 18 is to 30, the total amount, leaving off the RT. All right, that much is what came from the pressure, or that's the pressure that comes from the neon, or we can do it the other way, 12 out of the 30, which again, those reduce down to give us that 1.5 to 1 ratio. One part of the pressure came from the helium, 1.5 came from the neon.